Greetings, associates and fellow students. We are Group 710F, and we would like to welcome you to our official proposal report presentation. Without further ado, I'd like to hand it off to Ziad to start us off.
Hi, everyone. My name is Ziad Sultan, and I'm going to be starting off today by giving you the overall scope of the project and some of the various limitations we face as the group. So essentially, the basis of the project is that every year the Queen's Bridge building team is tasked with constructing a popsicle bridge that will be entered into competition. And this year, of course, is no different, except the COVID limitations that we face. Naturally, they came to the best design group in the school for help and tasked us with coming up with ideas for them to potentially use in the form of bridge models, as well as some research topics that they need help with. There's some specific limitations on what we can use. Are obviously we need to use 11.5 centimeter long by 1 centimeter wide popsicle sticks, and that wooden toothpicks and dental floss are permitted. However, other than that, we have complete creative freedom, and we're very excited about what we came up with. Overall, the group has made steady progress in the numerous ventures we were tasked with, and we're very excited to share the progress with our valued stakeholders and fellow students today. So yeah, next we have Jack speaking about one of the research topics I spoke about. So go ahead, Jack.
Thanks, Ziad. So just to give some background information before we present our ideas, every team member conducted thorough research on a specific aspect that will hopefully be included in our bridge design. We gathered info on 3 main points that are critical to our build: bridge types, popsicle sticks, and dental floss. For bridge types, the info obtained assisted the team in making a decision on what bridge design we would like to go with. For example, we found that the I-beam bridges are actually quite common due to their ability to withstand moments due to the high moment of inertia. Also, the bridge is simple to construct and can be built in almost any location. Additionally, suspension bridges, for example, require less material but are generally less stable as a result. And arch bridges are incredibly strong due to their ability to distribute force down the arch instead of just straight down. In addition to finding advantages of certain types of bridges, the disadvantages of each were also assessed and were taken into consideration when making our decision. As for popsicle sticks and dental floss, lots of research was done in order to fully understand all the physical properties of our most important and only building materials. We discovered that although thin and light, dental floss actually has a very high tensile strength, which makes it a good choice if one was to utilize cables in their build. However, one of the disadvantages of dental floss is that the strength range is very large depending on what floss you get, supporting as little as 2.5 newtons all the way up to 51 newtons, which makes it very unreliable. Additionally, lots of information was gathered on the paper birchwood that makes up the popsicle sticks we will be purchasing, including its specific gravity, modulus of elasticity, and impact bending. All this key information gathered allowed us to generate some ideas for what our bridge will look like and what materials we will be using to construct it. Please note that all the detailed information and exact values were posted in our Phase 2 document. I'd now like to hand over to Kai Wei to talk about some of our ideas.
So our main ideas is to create a bridge that contains both beauty and solidity. So to fit these 2 features, we have 3 characters. The first is arch and truss combination. In our structure, we use the arch to contain most of the loads. And the reason we use truss is to reduce the material using and to make the structure stronger. And for the bridge floor, we use the splicing board. At first, we choose to use the truss as our floor, and then we found that it's too hard to build. And the third one is our wooden structure uses mortise and tenon joint so that the hump can fit the groove perfectly. So the next will be our designs.
Yeah, so now we'd like you to take through the 3 of our various models that we made and speak a little about their specific niches and how they function overall. So first up, we have Harry speaking about the model he came up with. So yeah, go ahead.
So the idea behind this option was to combine many of the bridges researched to create a triple hybrid. Within this design, it is a combination of a truss bridge, an arch bridge, and a suspension bridge. The truss formation is seen at the bottom of the structure as the base, and also when looking at a top view, there are truss formations between the 2 arches. The suspension aspect is seen connecting different parts of the arch formation to the truss deck. This design is commonly known as a tied arch design and is all over the world due to its strength. The arch formation is seen spread across and is what is connected to the truss formation and what the suspension cables are attached to. This design allows for maximum load displacement and will distribute the force during the testing phase extremely well, going through the truss triangles, the arch beam, and the suspension cables. This design will come with its challenges, but is definitely a viable option and would be great to not let valuable research go to waste. I'm going to hand it off to Hayden to present the second option.
Thank you, Harry. When I was designing this bridge, I wanted to incorporate a Pratt truss and an arch. Pratt trusses in general are very sturdy and stiff, but they have one weak point, and that's in the center of the bridge. So with the arch is going to have an upwards force on the deck, while the weight will have a downwards force on the arch, and hopefully the forces balance out and distribute themselves nicely into the columns. And columns in this case are truss-like because I found that you can maximize and optimize cross-sectional area to create rigidness and stiffness of a solid column with a hollow column. But this design, while on paper is good, has a few issues, and the biggest issue is the weight. The design, when I drew a 3D model, is going to use too many popsicle sticks and go over the 6-gram weight, which is simply not acceptable, so revisions have to be made. Pass it off to Gabe.
Thank you, Hayden. My design here was based off very similar concepts to Harrison's design, as it incorporates 3 very popular bridge methods, suspension, truss, and arch. The difference is that instead of the suspension aspect hanging from the arch, it is suspended from 2 towers extending from the ground, and that instead of the platform being the contact with the ground, it is 2 bases from the arch that contact the ground. The advantage of this in comparison to Harrison is that weight is much more evenly distributed through the suspension members, but the issue with this is that it's far too complicated to create in the time we have allotted for the project. Next, we'll go to our final design with Hayden.
The amalgamation incorporates a combination of aspects from the different bridges shown previously. It is an arch bridge with a Pratt truss in the center. The way the Pratt truss will work is the forces, tensile and compressive, will be distributed through the arch at the connection points. The connection points are done by holes in the arch, and the Pratt truss pieces will be layered on top of each other with a pin connection from a popsicle stick pin holding everything in place. Once the forces are in the arch will then distribute them down to the base, and the base will return an upwards force on the arch, keeping everything balanced. There are horizontal beams that span across the bottom of the bridge beneath the deck, keeping the deck in place and trying to prevent cracking. We feel that this bridge is sturdy and utilizes enough elements from the previous bridge designs, as well as combats all their flaws, and will be designed with good construction ideas in mind. On to Gabe.
We've developed a very in-depth structure of how we're going to get work done. And to summarize it, it is basically that throughout this week, we hope to get half of phase 3 done, and we hope to finish it by the next week. With that, we'll complete the initial model and design and move on to creating a SolidWorks model, which we should get completed by the 28th of February in its most basic design. After that, we will run various tests on the SolidWorks and finish it in completion by the 10th of March and begin working on construction of the actual bridge by about the 25th of February. Once that is all done, we can work on finishing the actual structure of the bridge by the 10th of March, begin physical testing, and evaluate the effectiveness of our design and use it in actual bridge building competition like scenarios, and we will evaluate our findings for the final phase 4 and phase 5 report near the end of the semester. I'll hand it off to Harrison to talk about our testing.
So the testing will primarily be done using the CAD software SolidWorks. It'll be done using a simulation of stress tests that will be able to highlight the weak points of the design. From these, we are able to reevaluate and improve on the design. This will allow us to iterate over and over again until our design is perfect. Another option is designing a miniature model of our structure and to test it in person as we come back to campus. This will give us a very credible input as where the design is flawed and where it faults first. From here, the final design can be constructed, and then will be tested in the Queensbridge building team's workshop, in which a hydraulic press will be placed on a center point. Now I'll hand it off to Jack to finish us off.
Thank you, Harry. So in short, our team design will hopefully incorporate an arch build with a truss. As of right now, no problems have arisen with the project. However, later down the road, we may see some issues that we'll need to combat in terms of the SolidWorks, construction progress, and the design logistics. We'd like to thank you for listening to our client presentation. If you have any questions regarding our project design or implementation, please feel free to contact us at group710f@gmail.com. On behalf of the whole team, thank you for listening.